So in this video I'm going to introduce you to the definition of uniform continuity, and I want to compare it to the definition of normal continuity. So let's begin with a reminder of the definition of normal continuity. So for this, let's consider a function f that's a real valued function, and it's defined over some domain which we'll call D, and this domain is a subset of the real line. So it might be the whole real line, for example, or it could be a closed interval of the real line, or it could be some more complicated subset of the real line. And let's remind ourselves of the definition of point continuity now. So if we have a point P, which is inside our domain, then the meaning of the function f being continuous at this point P is that the limit of the function as x approaches P must equal the value of the function at P. And I've drawn a picture here to remind us of the intuitive meaning of that. So for the sake of our picture, I'm imagining that this closed bounded interval from A to B is our domain D. Here is our function plotted graphically, and here is our point P inside the domain, and here's where P is being mapped onto by the function f of P. And intuitively, what it means for the limit as x approaches P of the function to equal the value of the function is that as you approach P in the domain, as you get closer and closer to it, the value of the image of these points must get and stay indefinitely close to the value of the limit, which is the value of the function at P. So as you get closer and closer here, their corresponding image points, their points that they're being mapped onto in the codomain, are getting and staying indefinitely close to this value f of P. That's what it means for the value of the function to converge to this value as x approaches P. So that's point continuity, continuity at a single point in the domain. Now, what does it mean for the function to be continuous over the entire domain D? Well, that means that point continuity holds true for every single point in the domain. So for all P is an element of D, if this condition for point continuity holds true, then we would say that the function f is continuous over the entire domain. So in the example of the picture, our entire domain is this interval from A to B. So if for every single point in that interval it is true that the function is continuous at each one of them, then we would say that the function is continuous over that entire closed bounded interval. So for the normal definition then of continuity that we've seen in previous videos, you can talk about both continuity at a single point in your domain and then continuity over your entire domain. In the case of this new definition that we're about to make, uniform continuity, you never talk about uniform continuity at a single point. You would never hear someone say that a function is uniformly continuous at a point P. You only talk about uniform continuity over a set of points. So we can talk about uniform continuity over our entire domain of interest D. So what I now want to do is compare continuous over the domain D to uniformly continuous over the domain of interest D. So for this, what I want to do is actually write down this definition for continuous everywhere over the domain D in terms of the Epsilon Delta definition. So I've written that out here. So that for all P is an element of D has remained the same, and now I've converted this into the Epsilon Delta definition here. So for every single point in the domain, it must be the case that for all epsilon greater than 0, so however close you want to be to the value f of P, there must exist a delta greater than 0 such that for all x is an element of D, so crucially remember, we're talking about this domain D, this general domain of interest, and it might not be the entire real line, so of course we're only going to be interested in the real numbers that are actually in our domain of interest, because for the real numbers that are outside of that domain, the function might not even be defined. So for instance, these ones here, just to the left of A, if we're imagining this is our function, the function might not be defined for those values. So we're only interested in the x that is actually in the domain of interest where we know that the function is defined. So for all x is an element of D such that the distance between x and P is less than delta. So for all the points in the domain that are close enough to P, i.e. within delta closeness of p, it is then the case that if you look at what the distance between their image points is, so what the difference between f of x and f of p is, that will be less than epsilon. So the fact that however close you want to be, there exists a delta, you can find a delta, it might have to be very small, but you can find one that this does hold true for. That is the epsilon delta definition of the limit. Just to go into the intuition of this a little bit more to remind ourselves, so it's saying if this is our point P, and this is going to hold true for all P in our domain, then for all epsilon greater than 0, so that means however close you want to be to this value f of p, construct that epsilon interval around f of p here, f of p minus epsilon to f of p plus epsilon, then I can find you a delta such that if the point in the domain is within delta distance of p, and in the case of this point p that's nicely inside the interval, that's going to be an entire little delta interval around p. More generally, if for instance we're talking about one of these edge points like b, of course then it wouldn't be an entire interval, it would just be the half interval of the bits that are actually inside your domain of interest, which is what this bit here is capturing. But in the case of this point that is square inside of our domain, it's going to be an entire little delta interval around there. So you can find a delta that's small enough such that all the points that are within delta closeness, all these points in this delta interval, are mapped inside that epsilon interval around f of p. That's what this is capturing. Now, even though we have written delta here nice and simple as though it's just one number, remember it is not just one number. It is going to be different depending on what epsilon and what p-values you put in. So, of course, if you make epsilon smaller and smaller and smaller, closer and closer to 0, you're going to most likely require a smaller and smaller delta. So of course delta depends on epsilon, but also of course it depends on what point you actually are at within your domain of interest. So if you go to different points, the required delta for a given epsilon is probably going to be different. To hammer this point home even more, let's imagine taking a specific epsilon value. So consider epsilon is equal to 1 over 100, 0.01. What you could do is you could go to every single point in your domain, and we are assuming that the function is continuous everywhere over our domain, and therefore this will be true, so it will be possible to find a delta such that this property is true. Now, you can imagine that if you go to two different points in this domain, the delta is not going to be the same. In fact, as you go through the domain, you're going to get a huge number of different deltas, perhaps. And that is absolutely fine in the definition, the normal definition of continuity over an entire domain. You don't need the deltas for a given epsilon to be the same at every single point in the domain. That's what we're going to change in uniform continuity. In uniform continuity, we're going to demand that for a given epsilon, there is one delta to rule them all that will work for every single point in the domain. So here we go then, time for the definition of uniform continuity. So I've put a C here in a circle to remind us that this is the definition for normal continuity over the domain D. And now in a circle here you see uniform continuity over the domain D, and this is what is going to need to be true. So note that the for all P is an element of D no longer appears out the front. Instead, we start with for all epsilon greater than 0, there exists a delta greater than 0 such that, and now here's the for all P, for every point in the domain, and if you look at all the points in the domain then that are a distance away from that point P less than delta, then if you look at the distance between their two image points, it will be less than epsilon. So this is saying, given any epsilon, so for instance, epsilon is equal to 1 over 100, there is a delta which now only depends on epsilon, not P, such that if you go to every single one of the points in the domain D, and you look at the points that are also in the domain that are less than delta distance away from it, so you can imagine the delta interval around the point P, then if you look at the corresponding image points for points in that delta interval, they are inside the epsilon interval around f of P. It's saying that this delta works for absolutely every single one of the points P. So I've added in here now that delta only depends on epsilon. It's no longer dependent on the point P. So it will change for the epsilon, so the smaller you make epsilon, the smaller you will need to make delta most likely, but there's now a delta that works for all P's, so you don't have to change it for the different P's in the domain D. That's the crucial difference between this definition and this one. And by the way, this one is a stronger definition, a stronger condition analytically than this one. So what do I mean by that? Well, look at this definition for a little bit and you'll realise that any function that is uniformly continuous over its domain of interest is also going to be continuous over that domain of interest. So if it satisfies this, it most definitely satisfies this. Why is that the case? Well, here we're saying that for any epsilon, there is a delta that works for every single one of the points of the domain. Here we're saying for every single point of the domain, for every epsilon, you have to be able to find a delta that works and satisfies this. We'll just use the delta that works for every single one of the points for each of the single points. So you can prove this is true very easily from this one. Whereas the other way round, it is not true that this one necessarily implies this one, and I'll give you a counterexample of that now. So here is our counterexample. So our domain of interest is the open interval 0, 1, so not including the endpoint 0 and not including the endpoint 1. Now the fact that it doesn't include the endpoint 1 isn't important, but the fact that it doesn't include the endpoint 0 is. Now the function rule is then 1 over x, a function that I'm sure you're familiar with from calculus that I've attempted to graphically draw here. Now this function is actually continuous then over this entire domain 0, 1, and we can prove that using the algebra of limits for functions. So if we consider the limit as x approaches p of 1 over x, where p is some point in our interval 0, 1, then by the algebra of limits we can split this into the limit as x approaches p of 1 divided by the limit as x approaches p of x. Now there is a condition to be able to do that. It has to be the case that for this denominator function, for the point p that you're looking at, that there is an interval around that point P where the denominator function is not 0 anywhere on that interval. And of course that's going to be the case even if P is really, really close to 0, you can still find an epsilon small enough that if you look at that epsilon interval around P, that for that entire epsilon interval, this function x is not going to be 0 on it. So it does satisfy the criteria to be able to apply the algebra of limits in this way. So this limit is clearly 1, this limit is clearly p, so this is equal to 1 over p, so the limit of the function truly is the value of the function. So this function is continuous over its entire domain. Now the question is it uniformly continuous over this domain? And the answer is no, and let me explain intuitively why that is the case. So if it were uniformly continuous, then for a given epsilon there would have to be a delta such that this condition was satisfied for every single one of the points in this interval. But hopefully you can understand, if you think about a given epsilon interval here in the codomain, then as you get closer and closer to 0 in the domain, this function gets steeper and steeper and steeper. So the corresponding delta interval you're going to need here to land in an epsilon interval in the codomain is going to get narrower and narrower and narrower. So I've kind of drawn the picture larger here to try and explain this better. So if we consider this point P here in the domain, and here is f of P up here in the codomain, and then we're considering this little epsilon interval around f of P, you can see but the delta interval that you're going to need in order to land entirely in that epsilon interval over here is going to be extremely narrow. And as you actually bring this point closer and closer and closer to zero, this graph just gets steeper and steeper and steeper. It's an asymptote after all. So actually, that delta interval that you're going to need in order to land inside that epsilon interval is going to get narrower and narrower and narrower. So in fact, there's going to be no lower bound for the delta intervals. They're going to get smaller and smaller and smaller, indefinitely small in fact. So there can't ever exist some finite delta that is going to do for every single one of those points on that interval 0, 1. So I hope that example has helped to give you some understanding of why, even if a function is continuous everywhere over its domain, it might not obey this uniform continuity property over that entire domain. It might not be the case that there exists this one delta that will do the job for every single point on the domain.